Okay, let's get started. So let's continue to discuss more about the constant strength triangle element, the CST. In today's lecture, we will also give an example and we can work on that together on the board to solve these example problems about to get the displacement and strength field in a CST element based on the information given on the three nodes. Okay, and through doing this exercise, we can hope you can learn more and get familiar with the typical finite element analysis. And those kind of problem will we will be given in the quiz and exam as well. So make sure you can do it by yourself independently. Okay. Okay, so just a little bit of review of what we have discussed so far. Now, we have talked about the basic principles of finite element analysis, and we started with a fundamental element called the CST element, constant stress or constant strain triangle element. So here, if you can see my mouse, here is an element, CST element. It has three nodes, node 1, node 2, node 3, following the counterclockwise sequence, okay? Each node has 2 degrees of freedom. The 2 displacement in the one in the x direction called u1, one in the y direction called v1. And that element also has its own coordinates, x1 and y1. Same thing for the node 2 and node 3. Now, we have discussed using a polynomial equation to fit the displacement values in other points in the element other than on the node, okay? And we discussed the reason why we use the 3 terms polynomials to simulate the displacement field, okay? Because you have only 3 unknowns, you will have 3 unknowns to solve, and we only have 3 knowns in each degrees of freedom in this element, right? And that result in the linear distribution of the displacement we will get. And I have given you the examples, like on the roof, right? On this flat roof, if we know the height of each point of the 3 points, 3 nodes, and if we know the coordinate x and y of each point, we can exactly fit to find out the height of any point in this triangle. So this example is appropriate to this condition. Actually, using the CST elements is appropriate because the distribution, the height distribution on the roof is linear, and it can overlap with the triangle very well, and you can get the exact solution. Okay. We also give the example of the temperature. So here, the triangle may not be definitely it's not the best one. You need if you want to use the triangle element, you need to fine mesh it, get many triangles in this region, and then you can find out the detailed temperature variations in the any point. And remember, if you fine mesh these regions, every triangle element, you only have only on the node, only there are 3 nodes, you have the temperature values. Okay, and then if the point, if the city or town you are interested in are not falling onto the node of those triangles, then you will have to do the fitting. And it depends on how fine you mesh this area. Then it gives you the different accuracies of the temperatures variation. Okay, so this is just one examples, and of course you can use other types of the element to do the fitting as well. Now, within this element, how do we get the continuous mechanics values like stress, strain, and displacement? We also talked about it last time. So let's briefly review it. Now, suppose the displacement, continuous displacement, uxy, is written in terms of alpha1 plus alpha2x plus alpha1 3y. We can express alpha1, alpha2, alpha3, these three unknowns in terms of the known values. What the known here in this case are the coordinates x1, x2, x1, y1, x2, y2, x3, y3 of the three nodes, and the displacement on each nodes. Okay. Now, once we put those information in, we will write like u1. U1 can be written. U1 can be written as the alpha1, alpha2, x1, alpha1 plus alpha2, x1, plus alpha3, y1, and u2 write a similar way, u3 write a similar way. Then you can rewrite it in terms of the matrix notation, and then calculate it either in the MATLAB or in the finite element analysis softwares. Okay. Now we also explained the meaning, the physical meaning of this matrix in front of alpha vectors. So this actually is the transformation matrix, and the determinant of this matrix is equals to 2 times of the area of this element, these triangle elements. Okay, depending on what kind of elements you use. For triangle elements, that's the physical meaning is the area. But the different elements, they have a different meaning, and we will discuss that in the future lectures. Okay, so this always keep in mind case by case. For each different element, you have different specifications. Okay, you need to get very familiar with that. Don't confuse that. And also, in fact, in the real world calculations, you will prefer, depends on the experiment conditions, the mechanical loadings and mechanical boundary conditions, you will need to choose appropriate element types. Okay, we actually will learn that in the Abaqus tutorials online. Okay, so our goal is to express this continuous displacement field in terms of the shape function nxy times u1, n2, u2, n3, u3. Here, n1, n2, n3 are 3 shape functions, and then multiplied by the node displacement on 3 nodes. And our goal is to find out the n1, n2, and n3 from this equation, from the alpha1, alpha2, alpha3, because we don't want to get use those unknown. We want to use express them in terms of the shape functions. How to do that? So we have discussed about it already. This one, we can inverse this matrix, this non-singular matrix. And then alpha1, alpha2, alpha3, alpha vectors can be rewritten in terms of this form, the 1 over 2a. A is the area of the triangle. F1, F2, F3, B1, B2, B3, C1, C2, C3. This may inverse the matrix of this transformation matrix, and then times the 3 displacement. This displacement U vector, actually later you will know, and this is actually called a Q matrix. This matrix is the degree of freedom matrix. Okay, this finite element is based on the displacement. So you will get the displacement first. Once you have displacement, you calculate the strain by doing the differentiation, and then calculate the stress based on the constitutive relation and the material behaviors. Okay, so it's from the displacement to the strain, and then to the stress. Okay, and also to the force. Now, Here, this FBC, F is not false, okay? F is just a symbol. FBC, they actually are the simplified version. They actually represent the combination, special combination of the coordinates of the 3 points, okay? So F1 equals to this term. F2 equals to this term. F3 equals this term. Here, X and Y of the 3 nodes, they are actually all known. B1, B2, B3 depends on all the Y coordinates of the 3 nodes. C1, C2, C3 depends on the 3 X coordinates of the 3 nodes. Okay, they are in those forms. Area is half of the determinant of this term, this matrix, and I told, as we discussed already, this represents the cross product of 2 vectors. Okay, actually, it's to be more precise, actually, it's a cross product of 2 vectors, dot product with a unit vector. Okay, so this overall gives you the volume, but the height of that volume equals to 1. So this numerically, it also mathematically is also equals to the area of the 2 triangles. Okay, of the 2 triangles, and then half of that is 1 triangle equals to the area of the CST element. Okay. Now, from here, since we rewrite alpha in terms of another matrix and the node displacement of the 3 nodes, we can rewrite, and this one can also, of course, written in terms of the 3 equations. Putting these 3 equations into the original u, x, y function, and then that equals alpha 1, alpha 2, alpha 3, and alpha 2 and alpha 3 times x and y. Okay, x and y are variable. They can be x1, x2, x3, but they can also be other values within that triangle. Can also be on the boundary, on the edge of the triangle. Okay, so that means we are doing an interpolation. All the values are within that triangle. Okay, if it's outside the triangle, then it's called extrapolation. Extrapolation usually is pretty risky. You don't know what's the shape function outside. So sometimes if the x and y are too far away from the triangle, then it could be wrong. But if you're a little bit closer to the edge, maybe you still can believe that results approximately. Okay. Now, after we put these alpha functions in, then we can solve this equation and extract the u1, u2, u3 into the 3 terms, and then put the x and y continuous functions in front of them. So these 3 equations, respectively, are n1, n2, n3. They are function of x and y variables. These 3 equations actually are called shape function. So I can rewrite it, extract these 3 out, n1, n2, n3. They are actually the shape function. Okay, these are important. These are the key things you need to understand. And these shape function are particular for the CST element. For the later, when we talk about the rectangle function element, the shape function will be different, and that's also very interesting. Okay, it calls shape function because they are depending on the geometry. Later on in the future lecture, you will see how the rectangle shape element change those function. They have the different function. Okay, and also other different type of shapes, like quadratic, cubic elements. They all have different shape functions. Okay. So once we have those, for the y direction displacement v, the shape function is the same. So they will have the shape function times the v direction, the 3 node displacement. Okay. So overall, these 2 functions, u and v, they represent the continuous fitting functions that you can use to find out the displacement in any point in the triangle. Okay, because we derived these three functions, and they are all linear, right? They are all linear function of x and y. They only have one order, right? And they also have a rigid body constant values, right? Because they are all linear, this means the displacement within this element also is linearly distributed. So it's like this roof, the displacement are all linearly distributed. Another thing interesting here is, remember, the strain is actually the differentiation of the displacement. So if you differentiate those displacement function, you will actually get a constant value of the strain. Means within the square, not square, within the triangle, the strain is constant. If the strain is constant, stress equals to the C matrix, the stiffness matrix, material properties, times the strain is also constant. Okay, so I have talked about it briefly last time. We will talk more in the next few slides. Okay, but here from those shape function, when you in the future when you see those shape function, you will quickly realize that this is a linear distributed. This will contribute to a linear distributed displacement field. Okay. Now, that's what we learned about how to derive the equations that can be used to interpret the displacement distribution inside a CST element. Now, these two equations, U and V we talked about, they can also be written in terms of the matrix notation. So here, U and V, we can write it U equals to N1 times U1 N1 U1 plus N2 U2. So this here is the third term, N2 U2. So when you do the matrix multiplication, inner dimension always equal. So here is this is a 2 by 6 matrix, right? 2 means row, 2 rows. 6 means columns, 6 columns. 2 by 6 times 6 by 1. So this matrix is 6 rows, 1 column. 2 by 6 times 6 by 1 equals to 2 by 1. So here, it results in 2 by 1, so 2 rows, 1 columns, okay? And U displacement depends on the U, not depends on the V, right? Because U and V are perpendicular to each other. They are uncoupled, as we discussed earlier. So U equals to N1 times U1. So 6 times 6 correspondingly, N1 times U1, 0 times V1 means we do not, in the U displacement, it will not involve Y direction displacement V, okay? So N1 times U1 plus N2 times U2, and then no V2, N3 times U3, okay? For the V displacement, it will not involve U displacement, so equals to N1, same shape function, N1 times V1, 0 U2, no U2, N2 times V2, no U3, N3 times V3, okay? So you can write the displacement matrix, the continuous mapped displacement matrix in terms of another matrix, N matrix times the Q matrix. Q is the degree of freedom matrix, okay? So in this case, for any point in that triangle, you can put that the coordinates of that element xy into here. So N1, N2, N3 contains X and Y. So you can put the X and the Y into there and then times the constant. This is the constant matrix times constant. It will give you the displacement in that X and Y point. Okay. Now that's all for the calculation displacement fitting calculations in the CST element. Once we get this expression, we can use it to further calculate the strain. So so that strain is also approximate solution. Now to calculate strain, you can do the differentiations for the three strains. These three strains are the normal strain, epsilon XX around X direction, normal Y strain, epsilon YY, and shear strain, gamma XY in plane shear. Okay, all the components involve Z are all equal to 0 because these are all 2D conditions. So epsilon XX by definition, if you remember the definition from the elasticity, you take a very small element and stretch it, then to get the differentiate form of the strain. Epsilon XX equals to partial U, partial X. And U, we already know, U equals to this N, N shape function times the U, right? So it's actually equals to the sum of Ni, Ui. It means N1, U1 plus N2, U2 plus N3, U3. Now, as I just said, U are the constant, right? They're given X direction displacement. Now, N contains both X and Y. So when you do the partial differentiations with respect to X, N will take the partial. So it actually becomes a sum of partial Ni, partial X. And Ni, we already know that, as we write it here, Ni for the N1 equals to 1 over 2a F1 plus B1 X C1 Y. Okay, and remember F, B, and C. Remember that we put it here. They are all have they are the function of the no coordinates of these 3 points. So they are also the constant values for the F, B, and C. Right? They are all those X and Y on these 3 points are no. So they are the constant. The only unknown, only variable is X and Y. So they contain the X and Y linear function. So N take the X derivative equals to B. So N1 with partial N1, partial X, partial N1, partial X equals to B1 divided by 2A. X will get rid of, right? N2, partial N2, partial X equals to B2 over 2A. Here the Y, C1Y also get rid of, the C2Y also will disappear after differentiation. Partial N3, partial X equals to B3 over 2A. So that's why we can written them as BI over 2A. And then times Ui, that's the constant. Same thing for epsilon YY. We will have partial V, partial Y. That equals to Ci, C1, C2, C2, Ci divided by 2A. So it will become become Ci over 2A multiplied by Vi. Okay, so that's how we get the strain in the X direction, Y direction. And then you may note that all the variable X and Y disappear. So you get the constant value here. Gamma XY, the shear strain equals to partial U, partial Y plus partial V, partial X. Here we don't have 1 over 2. In the elasticity, you know that you usually have a partial 1 over 2, but we don't consider that for now. We consider this shear strength only have 2 terms. Okay. Now, partial u partial y equals to this term partial y. So then equals to ci equals 2a, c1 over 2a, c2 over 2a, c3 over 2a. And then partial v partial x, you will get a bi over 2a. So b1 over 2a, b2 over 2a, b3 over 2a, and all and multiply by v1, v2, v3 respectively. Okay, so like in the MATLAB, you will have a b1 b matrix dot star product the vi matrix. Okay, so now we get the 3 strength components, and they are all constant. Now, this also can be written in terms of the matrix notations. So you will have a strength. You write a strength as a 3×1 matrix, and then they can be written as a 3×6 matrix. B1, B2, B3, 0, C1, C2, C3, C1, B1, 2, C2, B2, C3, B3. This matrix 3×6 times the degree the Q matrix, the degree of freedom 6×1. Okay, this actually is coming from here. If you expand those together, explain all these 3 together, and then extract the U and V, then this equation set can be rewritten in terms of matrix form. And here altogether actually has 3 equations. So here also is 3 equations. Okay, but each equation has multiple terms. You have 3 terms here. These have 6 terms here. Okay, that's why here you have 3 non-zero constant here and 3 zero. Here is a 3 non-zero. But this guy you have a 6 non-zero constant. Okay, but they can be 0. If when you calculate, they can be 0. But when you write it, they can be represented by those symbols. This constant matrix called B matrix. Okay, this B matrix is used to calculate the strength in the CST element. This B matrix you can write as B in bracket, and the Q matrix, degree of freedom matrix, called Q in the bracing. Now, the B, we said all this already. The B matrix is a constant, and this gives the constant strength. Okay, so this we talk about this later. With the strength matrix, we can combine that with the material elasticity matrix, C matrix, to calculate the corresponding stress. So I hope you still remember in the elasticity class, and I can give I'll give some review on this as well. You for the linear homogeneous isotropic materials, when you express the elasticity matrix, you will have 6 components, and these 6 components, and in fact they can be written in a symmetric matrix. Okay, so this is a symmetric matrix. You will have 9 components, but in these 9 components, you only have 1, 2, 3, 4, 5, 6. These 6 values. Other 3, C1, 2, actually this one is called C21, actually equals to C12. C31 actually equals to C13. Okay, C32 should be equal to C23. And in fact, all these 6 components, if the material is linear elastic and homogeneous and isotropic continued, they can actually be further reduced to 2 components, two values, 2 constants. One is E, Young's modulus. One is mu, Poisson ratio. Okay, they can written in the respective forms. Now, for these 6 components, around the diagonal, you have the E Young's modulus, and G. G is also can be written as the E and Young's modulus, E and Poisson ratio is the shear modulus. So these, and on outside the diagonal, you have the C12 is a non-zero value. C13 and C23 are all zero because we don't have a out of plane z direction shear stress. Okay. Now, now the sigma xx equals to C11 times epsilon xx, C12 times epsilon yy, C13 times epsilon xy. In fact, that is the Hooke's law. Okay, that's equals to Hooke's law. Epsilon y, sigma yy equals to C12 times epsilon xx, C22 times epsilon yy, C23 gamma xy. Okay, and same thing for the shear component. Tau xy equals to C13 0 times epsilon xx, C23 0 times epsilon yy. So they are all disappeared. Plus C33 equals to G, shear modulus, times gamma xy. So shear strength only related to shear stress, no normal stress related. Okay, that is consistent. Now, given this C matrix, this is called a C matrix also, the elastic matrix, C matrix. Given the C matrix, it can times with the strain matrix. Strain matrix equals to B and Q, right? B matrix times degree of freedom, Q matrix, okay? So then the stress matrix equals 3 is 3 by 1 equals to elastic matrix 3 by 3 times B matrix 3 by 6, we just talked about, times the Q, the degree of freedom matrix 6 by 1. So it's U1 V1, U2 V2, U3 V3. Okay, so 3 by 3, 3 by 6, 6 by 1. Eventually give you 3 by 1, right? So that eventually give you the stress. Now, C matrix, as we see here, they are not the function of X and Y. So this is a constant. B matrix, we already talked about it in the CST elements, is also a constant, not the function of X and Y variables. Q is the degree of freedom, the node displacement in the 3 nodes also are constant. So eventually give you the stress is also constant. So every element actually will have one constant stress state. So the normal stress, shear stress are all constant. Okay. And of course, we don't have a Z component, we only have plane stress. So only the solid stress existing in the XY plane. This condition is called the plane stress. You may also remember you have the plane strain condition. These are two very important plane condition, 2D condition in the mechanics. Plane stress is actually for the plane are very thin. So all the stress are on the plane, not off the plane. Plane strain is for the plane or body really thick. So in the Z direction, because it's too thick, Z direction, you cannot have displacement. They're all constrained there. They're like clamped there. Around the Z direction is clamped. So no Z displacement, therefore no Z strain. But the Z direction stress is existing because if you use the Hooke's law, you can find if you confine all the Z direction strain, you still have the stress. Okay, we will talk about the plane strain in more depth in the next few lectures. Now, I want to go back to here. Now, here, what we will see is if we have an example that that is a plate. It's a plate that under the uniaxial stretch. Okay, you apply force on both ends. Don't need to consider how thick it is. Just maybe it's a finite thickness. Okay. Now in the XY direction, you will have a hole. If we have a hole inside this plate, then based on the mechanics, we will know when we stretch this plate, the stress distribution around this hole will have the stress concentration. If this is the perfect hole, the normal stress here around the stretching direction, maximum value, if it's a linear stress concentration factor equals to 3, okay? Means the stress here is 3 times more than the far field stress applied. Now, because the stress here is changing, is concentrated very quickly. If you mesh this plate, use one type of element with the same size. So this is a CST element. You put this CST element on at the neighborhood of this hole. You also have this, use the same element at the far field. Then here I only draw a few elements, but you will, once you mesh, you actually have everywhere meshed. I just give you a simple demonstration. Now, based on our understanding, within the CST element, stress will be a constant. That means within this element, stress here close to the circle equals to the stress here, which is farther away from the hole. That will cause some trouble because stress concentration locally existing here and gradually decay to as the distance further away from the circle. You need, if you use only one big element to represent that change, this element give you the constant stress. It will not show any trend, any change of the trend. So that will lose the accuracy of the analysis. That's why using those bigger CST element, coarse CST element, you will not capture the stress concentration. Okay, so to overcome that problem, if you still want to use CST element, but you don't want to encounter this trouble, then one thing you can do is to non-uniformly mesh the plate, meaning you can make the CST element smaller, closer to the hole of this plate, and then gradually increase to the far field. In the far field, if you use a large element, that's fine because you will have uniform stress applied, and the CST element around here, actually stress will be concentrated. Stress will be uniformly distributed, like a like stretching a uniform bar. All the stress in the bar will be constant, right? But if you have a hole there, if a defect there, around that defect, the stress will concentrate, and they have different values. Okay. So in the EPICS tutorial 5, you actually can learn in the graphic interface how you can mesh the region close to the circle more densely, and then gradually increase the mesh size, increase element size to the regions further away from the defects. You can, of course, make the whole plate very dense, but then the problem is you will need a lot of computation power. As the element becomes smaller and smaller, you will have more nodes on the plate, and each node you need to solve the differential equations. So it takes more time for you to get the results, right? So ideally, people want to, here is one example. Here, people want to do the the finer mesh closer to the defects, and then gradually increase the mesh size, and with the accuracy ensured, okay, to reduce the computational price. You can also, because this is a symmetric problem, you see this is around the x direction, this is symmetric. So this part and this part actually are symmetric. Around the y direction, this part and this part also symmetric. So if you calculate only a quarter of this plate, you can capture all the essential mechanical properties, mechanical characteristics. So here, to further reduce the computational price cost, you can just simulate a quarter of it, and then use the fine mesh and the coarse mesh combination. In the tutorial 5, you will learn how to do this mesh. This is called a radial mesh. So around the radius, you can make different mesh. Here, this problem, you can also gradually increase the mesh around the radius, and then choose different type of the elements depending on your understanding of the problem. You can choose different elements to get the best approximations. Okay. So that's actually here what I hope to introduce to you is that's the reason because of the properties of those elements. You need to you can best optimize the problem solving process. So a good solution, the best solution, depends on your deep understanding of this mechanics problem and the properties of the element you can use, and then combine them together. You can get first they get a very beautiful mesh. So visually very beautiful. So it's very organized and very decent. And then scientifically, you can get a very precise results on the object. Okay, and then you will do a great job. Okay, so a few more things about the CST element before we do an example problem together. So we have several minutes, 10 minutes left. Okay, we should be okay. Now, for the CST element, since the displacement actually is linear, the triangle elements, when they deform, they will actually not deform in a curved way. They will also remain as a triangle, but with different shape. So like one triangle get stretched, or one triangle get crushed, not crushed to a line, but get compressed. But they will not become circular shape, will not become curved, right? In that case, if within the triangle you have any straight line, after the deformation, the line will still remain as a line. It will not become a curve. It will not become break. Okay, line still remain a line. Only thing changes the magnitude of the line, the length of the line, or the direction, the angle, the direction of the line get changed. Now, in that case, in this case, we one more word. Actually, based on this, what I said, you can see the simplicity of the CST element, but you may also realize for the CST element, they have limitations, because in the real world, not all the deformation are linear. So if you use the CST element to simulate some nonlinear deformation, you actually are far further away from the exact solution. Okay. So you need to choose different element. Some either make the CST element as a quadratic, add more nodes there, or choose square-shaped or different shaped elements to fit your problem. Now, this is a one CST element. Now, consider this element has 3 nodes, 1, 2, 3. Let's think about the displacement around one edge of the element. Okay, so around this edge of element, since the displacement, as we said, is linearly distributed. If we know the displacement value of a point A, point 1, and point 2, we can actually do a linear fitting very quickly to know any point, the displacement of any point around this line. In other words, the displacement either U or V displacement around this line actually only depends on the U and the V displacement of point A, point 1, and point 2. It has nothing to do with point 3. If you choose the point outside of this line, maybe into the element, then number 3 displacement, their displacement get involved. But if along the line 1 and 2, then only these 2 nodes are involved. Same thing happened for node 1 and 3. If you choose a point around this line, on this edge, then only the displacement of 1 and displacement of 2 or 3 are involved. Okay. In that case, the displacement of any point on this line actually can be written as U phi. So phi is the distance of that point away from the 1. If this edge is equal to the length is A, then this phi change, this phi, this value change from zero, starting from 1 to A when it overlaps with the node 2. Okay, so then you only the displacement on 1 and 2 are known. Only variable is the phi, the distance of this point away from the number 1 node. Then the U actually can be written as the constant gamma 1 plus constant gamma 2 phi available. V can be written as the constant gamma 3 plus V gamma 4 constant times phi, right? So then it becomes much simpler. So if we can write this, if you can understand this, then for those 4 constants, we can actually calculate them just as we calculated alpha 1, alpha 2, and alpha 3 when we derive shape functions earlier. Now, this U phi, so displacement, U equals to, you can write as 1 minus phi over A U1 plus phi over A U2, okay? We can check it together. If phi equal to 0, means phi at a point, this red dot, this here, I write 2 elements here. I draw 2 elements here. Don't worry about it. I will explain shortly why I draw here. Now, let's look at this top element first. If this phi equals to 0, means this dot is on the node 1. Then here equals to U1, phi equals 0, right? Equal U1, phi equals 0. So here, this term equals 0. So U phi or equal to U1. So that matches with displacement on the node 1. If the phi equals to A, because the distance equals to A, then A over A equals 1, 1 minus 1, 0. So this term disappears. 1 over A, or A over A, 1 equals U2. So it overlaps with U2 and the displacement equals to U2. So that matches. Same thing for the V. The V direction, the Y direction displacement of this point, also 1 over 1 minus phi A times V1 plus phi over A V2, right? So this matches with the point 1 and point 2 when the phi changes. And then in the between, they are linearly distributed, okay? Now, so this actually, now this is the function. these two are the functions to represent the displacement of any point on the edge of this CST element. Now, why this is important? Why I'm asking this? The reason why we do this, the reason is there's always a question when you think about it. When you mesh an object, you are not mesh it with one element. You have many, many elements, like here. Many, many elements to mesh an object. There's any line here, any edges here actually are shared by the two elements. Any edge, if you consider 2D case, shared by these two. There will be always a question. If you have a point here, like here, if you have a, like here, two elements, element 1, element 2. If you have an element, if you have a point on this edge, you determine the displacement of this point based on the shape function and the three nodes coordinates and the displacement values. This point also shared by this element. And if you calculate the displacement of this point, you will not use the shape function of this element and the displacement of these three nodes, right? These nodes actually is different. Node 2, this node 2 of this element 2 is different from the node 3 of element 1. So always people will ask, is it possible that the displacement I calculated here based on information in this element is different from the displacement of this point calculated by the information of this element? If they are different, then means in one point, they have two displacement field. That means this point is broken. So it has a crack there. It separated from each other. They have different values. It's discontinued. That is not allowed in our discussion in the current finite element course we discussed. So these 2 points, when you calculate that, the displacement has to be the same. What can then be same? Can that then be the same? The answer is yes, because around this line, this point only depends on these two ends, these two nodes. Also for this guy, these two nodes, and these two nodes are shared nodes. They have the same displacement field, displacement value, and the coordinates, and nothing to do with the remaining node. Okay? So you really be assured that at this point you will have unique displacement values. Okay, but that's only for displacement. That's only for displacement, and that is called inter-element displacement compatibility. Okay, that is satisfied. For the strain and stress, they are not compatible. Here you have one strain and one stress in over this element, and it may not be equal to the stress and strain in this element. So over the boundary, you have a jump. Okay, you could have a jump. Okay, so that's what I described. That's an important compatibility you need to keep in mind. Okay, so those notes you can read them later on. I just want to explain to you in the essential points you need to understand. Okay. Now let's together, based on what we described, the CST element calculation from the coordinate displacement of the 3 nodes, how we calculate the displacement field, stress field, strain field of any point in an element. Okay, so let's do an example together. So here is one example. Now, this one has 2 elements. So the 2 triangles together, they form a square. They have element 1, element 2. They share one edge. For element 1, they have 3 nodes, node 1, node 2, and they also form a node 4. okay, node 4. Node 4 and node 2 are shared with the element 2. Element 2 has 3 nodes, node 2, node 3, node 4. And they have corresponding coordinates. For the node 1, you have the coordinates 0, 0. Node 2, you have coordinates 1, 0. Node 3, you have coordinates 1, 1. Node 4, you have coordinates 1, 0, right? So this for this square, the edge length equals to 1, okay? And they have a inter-element edge between node 4 and node 2 to give you 2 triangle elements. Now, if given the displacement of 4 nodes, so you have U1, V1 for the node 1, given, which equals minus 0.1, 0. U2, V2, the displacement on the node 2 equals to 0.1 and 0. U3, V3 equals to minus 0.1, 0 for the node 3. U4, V4, 0.1 and 0 for the node 4. If you are given the displacement for all 4 nodes, how to calculate the displacement of any other node, other point within these 2 elements, and also the strength within these 2 elements. Okay, so let's calculate this together. One thing you need to keep in mind is when you calculate those conditions, you need to calculate element by element. 2 elements cannot be shared, cannot be calculated using the same information. They actually is case by case. Okay, so let's calculate the shape functions in the element 1 first, and then we can calculate the shape. You can calculate the shape function in element 2 by yourself. I have the answer solutions in the slides. You can calculate that and then compare with that. Okay, and then from those shape function, from those equations, the U and V displacement field, you can calculate the strength field in each element respectively. Okay, so how to calculate let's do the element 1 first. How to calculate the element 1? Now, for the still remember what we did before, what we will use, the input will be the displacement value of the point involved in the element, and the coordinates of the nodes in that element. Using those input, we will calculate F, B, C. They are the constant, F, B, and C. Those 3 components in F, 3 components in B, 3 components in C. They are all constant. We will calculate those 3 vectors. Use these 3. We will put that into the shape function. Still remember the shape function, the N1, N2, N3. They are the FB and C, FB and C, and also the node U functions. And then you have X and Y, right? Then we calculate the shape function. For the shape function, you can calculate the U and V, right? Here, actually in the matrix form is U and V right here. Okay, let's calculate those together. Now, let me share change the screen. Okay, let me share the screen. Okay, I have already written here. So here, here are 2 elements. Let's calculate the element 1 first. Okay, element 1 in the brace, and then they have 3 nodes: 1, 2, 3, 1, 2, 4, 1, 2, 4. Number 3 nodes is not involved, so you should not use number 3 to calculate the element number 1. Okay. Now you know the coordinates of node 1, node 2, node 4. We also know displacement of node 1, node 2, and node 4 already, right? Now, let's firstly calculate the shape function. To calculate the shape function, we need to calculate f, b, c. So the formula, the equations, I written them in the black color. The value of the elements we use are written then in the blue, and the results are also written in the blue. I write because you need to pay attention. Here, you only use the node 4, not node 3. So this one, node 4 information, I written then in the red color. So this is a common mistake many students will make. Now, for the f, to calculate f, f1 equals to x2 y3 minus x3 y2. Okay, x2 equals to the x coordinates of node 2 is 1. y3 here, although we write as y3, this actually means the third node. In this case, the third node is node 4. So we should write the y coordinates of node 4, which equals to 1. And then minus x3 times y2. x3 is the node 4's x coordinates. y2 is the y coordinates of node 2. Both are 0. So 1 times 1 minus 0 times 0 equals to 1. So f1 equals 1. f2 is x3, the x coordinates of node 4, times y1, y coordinates of node 1. So it's 0. And x1 times x1 y3, 0 times 1, right? 0 here times 1 here. Okay. So the f2 equals 0. f3 equals to x1 y2 minus x2 y1. So you can do the same thing, you get a 0. Okay. That's how you calculate the f vectors. So you get the 3 values, particularly for this element 1. b equals b1 equals to y2 minus y3. Again, the y3 is the y coordinates of element 4. Okay. Now minus 1, 0 minus 1 equals to minus 1. b2, you can use corresponding results expression in the slides, equals to 1. b3 equals to 0. c1 equals to c3 minus x2 equals to 0 minus 1 equals to minus 1. c2 is 0. c3 equals to 1. Okay, you can put the value in to calculate that. So then you have all the constant components needed to calculate the shape function. Then you another one is the area displacement area involved. Area equals to 1/2 determinant of the matrix, the transformation matrix I talked about. You can put the here involve x1, x2, x3. Here x3 is the x coordinate of node 4, and y3 is the y coordinates of node 4. Okay, you can put those values, those coordinates in, and then calculate the determinant. That's fine. But here, as I just mentioned, this guy actually equals to this determinant of this matrix equals to the area, twice the area of this triangle CST element. So that twice of this equals to this square, the area of this square. equals 1 times 1. And then half of that equals to 1/2. So A actually equals to 1/2. So that's very quick. You don't need to put it, if you understand the physical meaning of this matrix, you can quickly calculate the A. Okay. With that, we have the three shape functions. N1 is 1 over 2A, and then the function of F1, B1, X, C1, Y. Right? N2, you can write the expression. They're all in our slides. N3, you can have this expression. Now, input the value we just calculated specifically for the element 1. So F1, we calculated that. B1, we calculated here. C1, we calculated here. And then they are the function of the X. Okay. That means, and 2A, we already know 1/2. So this one is 1 now. Okay, so this term is 2 times 1/2 equals to 1. Okay, so this is cancelled out. This guy, N, so the N1 eventually equals to 1 minus X minus Y. Okay, so that's good. You can check that's linear equations. N2 equals to is also 1 times F2, B2 X equals to X, and C2Y equals to C2 is 0, so 0 Y equals 0. So this guy equals to what's remaining here equals to X. Okay. For N3 here equals 1, and F3 we calculate equals to 0 here. B3 times X, B3 equals 0, so this also 0. This equals to 1 times Y, so it only equals to Y. Okay, so that's how you calculate the N1, N2, N3. These three important shape function for the CST element. Now, from here, you can find out the continuous fitting function, the U, V. So U will be N1, U1 times N2, U2 plus N2, U2 plus N3, U3. So N1 is 1 minus X minus Y times U1. U1 is the U displacement of node 1. It's minus 0.1. N2 is X. We calculate X times U2 is 0.1. Okay, 0.1. And then N3 equals to Y times U3. Here, U3 is actually the displacement of node 4. Okay? This is red colored. Together, what does this mean? Together, it will equal to, so this will be minus is 0.1x plus 0.1y. Here is also 0.1x. 0.1y. So together would be 0.2x plus y. And then minus a term, minus 0.1. Right? That's the U displacement field. This is a linear function. V equals N1. N1 is the same shape function. V1 equals to 0. N2x V2 equals 0. N3 is Y times V3, which is the V displacement for node 4. Okay, equals to 0. It's given here. So overall, this equal to 0. These actually are the important value you will like. Okay? These two are very important. Because then you can find out any displacement. You can actually try it. You can find any displacement on any point within this triangle. Okay? Now, with this, we can further calculate the strain field. So the epsilon for this element 1, epsilon xx is partial u, partial x. U we already know is this one. So this one, if you do the partial u, partial x, this equals to how much? 0.2. So 0.2, right? epsilon y is the partial v, partial y. So partial v is 0 actually. So this is equal to 0. Okay. Gamma xy equals to partial u, partial y. Partial u, partial y is equals to 0.2. And then partial v, partial x equals to 0. So this also equals to 0.2. Right? This gives you the constant value of x direction strength and the shear strength in this element. So they are the constant value. That means within this element, all the values are the same. Okay? And then given the material behavior, material properties, you can calculate the stress. So that's how you calculate the displacement, strength, and in the future we will show you how to calculate stress within the given CST element. Now you can also try it in the element 2. Then your x1, x2, x3, or y1, y2, y3 will be the element 2, element 3, element 4, respectively. You make sure you add the correct coordinates, correct displacement into these F, B, C functions, and then A will be the same because this is the same area. And then add that into the shape functions, get the shape function, and then calculate the U and V in this element. And then further, from the U and V, you can do the differentiation, get the strength, 3 strength components in the element 2. Okay, so this is how we calculate by hand how to do that. Okay. Okay, so I think that time is over, and let's continue next time.